Right now, physics is basically two masterpieces that don't speak the same language. On one side, quantum physics. It's our best set of rules for tiny things. Electrons, atoms, the particles we smash in accelerators. It predicts outcomes with almost unbelievable precision. On the other side, gravity, Einstein's general relativity. It's our best set of rules for big things: planets, stars, galaxies, black holes, and even ripples in space-time itself. And here's the part where things don't add up. The universe is not split into tiny mode and big mode. Real places exist where you need both at once. The center of a black hole, the first moments after the Big Bang. The edges of extreme gravity where space-time is curved hard, but the ingredients are still quantum. When we try to describe gravity using quantum rules the same way we describe the other forces, the calculations blow up. The numbers run to infinity in a way that refuses to be fixed. It's like the math is telling us, you're describing the world with the wrong basic pieces. String theory is one of the most ambitious attempts to replace those basic pieces, so gravity and quantum physics can finally fit inside one consistent story. Imagine you have a smooth sheet representing spacetime, and you place a heavy ball on it. The sheet dips, roll a marble nearby, and it curves toward the dip, not because something pulls it through empty space, but because the surface it moves on is curved. That's the basic picture of general relativity. Mass and energy shape spacetime, and motion follows that shape. Now, shrink your view smaller and smaller until you're looking at space-time at absurdly tiny distances. Quantum physics tells you nothing down there is perfectly still. Fields fluctuate, energy briefly appears and disappears. Outcomes become probabilities. So the question becomes very concrete. What does gravity look like at that scale? What does curvature mean when the fabric itself is jittering? In particle physics, we usually start with point-like particles. No size, no internal structure, just a dot. But if you treat gravity the same way and push the math into extreme conditions, you hit those ugly infinities. String theory suggests a different starting point. What if the most fundamental thing isn't a dot, but a tiny one-dimensional string? Not a rope you can see, not even close, but something with length and no width, so small it would be invisible to any microscope we can realistically imagine building. A string can vibrate in different patterns. It can move through space. It can split into two strings. Two strings can join into one. And the key idea is that different vibration patterns show up to us as different particles. In this view, an electron and a photon aren't two separate kinds of dot. They're the same kind of object playing different vibration modes, like different notes produced by the same underlying instrument. When you write down the equations for vibrating strings, one of the allowed vibration patterns behaves exactly like a particle with the right properties to carry gravity. Physicists describe it as a massless spin-2 particle, which is basically the exact signature you'd expect from a graviton, the hypothetical quantum carrier of gravity. So gravity isn't being glued on as an afterthought. It shows up naturally once you accept strings as the fundamental object. That's one of the reasons string theory became such a big deal. It offers a framework where quantum physics and gravity can coexist without the math immediately collapsing. Strings also come in two basic types. Some are open, like tiny segments with endpoints. Some are closed, like tiny loops with no endpoints. In many versions of the theory, closed loops are linked to gravity. Open strings are linked to other particles, including many force carriers, especially when those open strings have endpoints that can attach to higher dimensional surfaces. And now we hit one of the most famous, most mind-bending requirements of string theory: extra dimensions. If you want the equations to be consistent, strings don't like living in only 3 dimensions of space plus time. Many versions require 10 total dimensions, and some extensions point to 11. That's not a fun add-on. It's a structural requirement of making the math behave. So where are these extra dimensions? The idea is that they're compactified, curled up so tightly that we don't experience them in everyday life. String theory suggests space might have extra wrapped directions at every point, but on scales so tiny that we normally glide past them without noticing. Here's the next step. The shape of those hidden dimensions isn't arbitrary. The geometry can be incredibly complex, and in many models, it's described by special curled shapes, and that geometry can influence which particles exist, their masses, and how strongly they interact. In other words, the microscopic shape of space itself could help determine the particle menu we observe. To keep the mathematics stable, many string theory versions also include supersymmetry, the idea that particles of matter and particles that carry forces come in partner pairs. In a supersymmetric world, every known particle would have a heavier partner. We haven't observed those partners yet, which means if supersymmetry is real, it's hidden at energies we haven't reached so far. But in the string theory story, it often appears as part of what makes the whole structure consistent. String theory doesn't automatically give you one unique universe. It produces an enormous number of mathematically allowed solutions because there are so many ways the extra dimensions can be curled. This is often called the string landscape. And once you have a landscape, a question naturally appears. If the theory allows an immense number of possible physics settings, why do we see this specific universe with these specific laws? This is also where the multiverse idea gets pulled into the conversation. The reasoning goes like this. If string theory allows many stable configurations, then it's possible that different regions of a much larger reality could settle into different configurations, different shapes for the hidden dimensions, different particle properties, different strengths of forces. Each configuration would behave like its own universe with its own consistent rules. So, in this picture, the multiverse isn't just a philosophical daydream, it's a possible consequence of having too many consistent solutions inside the same deep framework. Our universe would be one address inside a gigantic menu of allowed realities. So, why do people still care about it? And what would change if string theory is actually correct? If string theory is right, it would mean we've finally found a mathematically consistent way to describe the most extreme places in the universe without the equations tearing themselves apart. We'd be able to talk about the earliest instance after the Big Bang using one unified framework instead of switching between incompatible rulebooks. We'd have a clean quantum description of gravity, which is exactly what you need to understand what space-time is made of at the smallest scale. It would also mean black holes aren't just mysterious objects that swallow everything into a void. A correct quantum gravity theory would tell us what happens to information, how entropy and geometry are related, and what the inside of a black hole really means in physical terms. And the real-world impact might not look like string-powered gadgets, at least not soon, but it would be huge in a deeper way. History shows that when we upgrade our fundamental understanding, new technology eventually follows, often in ways no one predicts at the time. A complete theory that unifies quantum physics with gravity would reshape our ability to model extreme matter, extreme energy, and possibly even the structure of space-time itself. It would upgrade the foundation beneath everything we do in physics, from particle theory to cosmology to quantum information. Here's the short version to keep in your head. We have two perfect rulebooks, quantum physics and gravity, and they clash exactly where the universe gets most extreme. String theory says the smallest building blocks aren't point-like dots, but tiny vibrating strings. And gravity appears naturally as one of their vibration modes. To make the math consistent, extra dimensions appear, and their hidden geometry can shape the physics we observe. And because the theory allows many consistent solutions, it opens the door to a multiverse-like landscape of possible universes. That's it. If you like the video, subscribe for more quantum stuff.